Dear student, we left our discussion at the electric field because charges attract and repel each other due to the field present between them, and that field is called the electric field. Now we try to understand what is this electric field and how can we quantitatively measure it. You can understand the electric field. For example, we consider a charge Q and another test charge small q. So this test charge experience a force of repulsion from the positive charge. So arrow represents the direction of the force and the length represents the magnitude of the force. If I move the charge a little away, then it still experience a force of repulsion but with a lesser magnitude. And if I take it to further away, then it experiences a more smaller force. And if we take it more away, then it won't experience any kind of force. So we can say that there is a region around this charge, capital Q, where it can apply a force, an electric force on another test charge. Then this region is called an electric field. But the effect of force is not same at every location inside this field. So the strength of field is different at different locations inside the field. So we now will try to understand how to find what is the strength of the field at different location closer to the charge. We use electric field lines to express the presence of electric field. So here what we are using is a positive charge closer to a negative charge, and we can see the direction of force on a test positive charge due to a positive charge Q and a negative charge Q is different. The arrow shows the direction of the force, and the direction of the force actually defines the direction of the electric field. So we can say for a positive charge, the electric field is away from the positive charge, and for the negative charge, it's defined towards the negative charge. Therefore, for a point positive charge and for point negative charge, we can represent the electric field lines in this way. And if we place two negative charges close to each other, or a positive charge and a negative charge close to each other, then they adjust the electric field in such a way. So we can see a positive charge and a negative charge, this one and that one, this the electric field lines support each other, so they attract each other. And for the charges which both are negative, the electric field lines they don't support each other, so they repel each other. Point charge means a charge that cannot be further divided. So we can take an electron as a point charge, a proton as a point charge. For a positive charge, we can define a circle around it, and on the circle, I can consider a point A. And the field has a strength EA here, and at a point B, it's defined as EB. At point B, a test charge experience a lesser force as compared to at point A. So we can say that the strength of the field at A is more than the strength at B. But why the strength is different and why the force is different? The easiest way to understand is at point A, you can see on this circle, the electric field lines are closer as compared to at point P. So here they are more further away and here they are closer. So the strength and density of the field lines, they define the strength of the field. Therefore, more closer the electric field lines, more stronger the electric field is and more stronger the electric force will be. So we define the strength of the field with the help of density of the electric field lines at that place. So for example, in these kind of situations, you can see we can easily say that at a same distance from A, B and C, the strength of the electric field is different. For example, 1 centimeter away from A, B and C, the density of the electric field lines is different. Hence, the strength of the electric field lines at the same distance from A, B and C is different. Also, we can see that as we go away from charges A, B and C, the separation between the field line changes. What about in this region? I'm talking about here. So you can see we have a positively charged plate and a negatively charged plate. In this region, everywhere the separation between the field lines is same. It doesn't change. It means the field is same everywhere, and this we call uniform electric field. So the field over here is uniform. So in order to have a uniform electric field, usually we place two oppositely charged metal plates in front of each other at a distance. So between them the electric field is uniform. At the edges it's not. So at this place and at this place the electric field is not uniform. So we can have the electric field lines wherever there are charges, and we can define the field strength according to the density of the electric field lines. Now the thing is, we cannot see the electric field lines. So how could we get the experimental evidence of the presence of the electric field lines? So for that, we use an experiment that is called a Semolina experiment. So if you write on YouTube this electric field demo with castor oil and semolina seeds, so what we do, we take two rods placed with a high voltage power supply. On one side it's attached to the positive, on the other it's negative. So usually red is taken as positive and black is negative. So they are attached to the high voltage power supply, and we put in the dish a castor oil. Castor oil is usually used in food. Then we put semolina seeds. They are very small in size, usually used in food. Um, In some countries, the halwa is made from semolina seeds. So, so as long as we put some semolina seeds, they actually take the shape and they are aligned in a direction. So in this experiment, because we are using the straight rods, so semolina seeds are aligned in straight lines. So I suggest you to see this video on a YouTube and see how the semolina seeds align, and then you will need it means the semolina seeds are charged inside the electric field and they experience a force in the direction of the electric field. Hence, they are aligned in the direction of electric field. So, their alignment is an evidence of the electric field or the presence of the electric field over there. So, yet now we can say that the electric field surrounds the charges in a region where they can apply force on the other charges. The electric field lines are used to represent the electric field, and electric field lines are drawn away from the positive charge and towards the negative charge. The field lines indicate the direction of the electric field. Closer the electric field lines, the stronger the magnitude of the electric field. An electric field line starts on a positive charge and ends on a negative charge if they are placed closer to each other, like this example. So we have a positive charge and a negative charge placed close to each other. When we put a positive charge somewhere, so you can see the positive charge moves from a positive charge towards the negative charge. It means it moves in the direction of the electric field lines. So positive charge experience a force in the direction of the electric field, and the negative charge experience a force opposite to the direction of electric field. And anywhere else if we place they the charge move along the field either towards or away. It depends upon whether it's a negative charge or a positive charge, but the charges experience the electric force along the electric field. So here the positive charge, this one, will not actually go in a straight line like this, but it will move on this electric field line. So they experience a force along the field lines. So field lines show the direction of the force experienced by a charge. Okay, how to define the strength of an electric field? So we can take an example that this equation everyone knows, and if I change this in this way, W is a gravitational force and it acts on a mass. So gravitational force per unit mass is the gravitational field strength. So G is gravitational field strength because the gravitational force act on the masses. So field is defined as the force per unit mass. Similarly, the strength of the electric field. So electric field exert an electric force that act on the charges. Therefore, the electric field strength is defined as electric force per unit charge. That's known as electric field strength. Force is measured in coulomb charge is measured, Newton, and charge is measured in Coulomb. So the electric field strength has an as SI unit as Newton per Coulomb. Similarly, from here, I can say that the electric force is equal to QE. F here is the electric force. According to Newton's second law, every force is equal to mass multiplied with acceleration. Therefore, the acceleration experienced by the charge q inside an electric field is given by and we know acceleration is F over m. So this is QE is the electric force. So if we want to find the acceleration of a charge q having a mass m inside an electric field E, we can use this equation. If the electric field is constant, then acceleration is constant. But if the electric field is not uniform, then the acceleration will be non-uniform, different at different locations. So for example, an electric charge, this value, mass that value, is placed inside a uniform electric field of strength that near to the negative plate as shown in the figure. So you are asked to find acceleration gained by the electron. So the acceleration, as I said, the charge will experience a force which is equal to QE, and every force is mass into acceleration. So hence acceleration is QE over m. So Q is 1.6 into 10 power minus 19 Coulomb. Electric field is given 100 Newton per Coulomb. And mass is 9.1 into 10 power minus 31 kilogram. So here you will find the acceleration in meter per second square. There you can find it, as I'll leave for you. Now the second part is asked the final velocity with which it will reach to the positive plate. So we assume that it starts its motion from rest and it moves actually from the negative plate to the positive plate. Because the electric field is uniform in this region, it means the electric force is also uniform. It means the acceleration is uniform. If the acceleration is uniform, we can use the equations of kinematics. And you know, the equations of kinematics are only possible if the value of the acceleration is constant. So here, the value of acceleration is constant, so we can use an appropriate equation of kinematics, and in this situation, we can use that one because it starts from rest. So V will be equal to 2as square root, and 2 into a, and a you will find from the first part, and the distance that is provided over here 25 centimeter, I write in meter 0.25, and then we can find the value in meter per second. Okay, so in this lesson you understood what is an electric field and how can we define the strength of an electric field when we can consider the electric field constant, uniform, and in what situations the electric field changes with the distance. So for a point charge, as a summary, I tell you, the point charge, the electric field is non-uniform for a point charge, but when you have two oppositely charged plates, so we can have a uniform electric field. In the next video, we will talk about the forces, the electric force between two charges.